neck twisters, spine shakers. Rides like this are a lot of fun once in a while and for some people, but few of us would like to do very much traveling over the waves of a roller coaster. These are only a few of the devices that man has invented to give himself a thrill and a pain in the neck. Sudden ups and downs are all right in an amusement device, but automobiles haven't much use for them. The automobile engineers know that in our motor cars, we want comfort and a smooth, level ride. Even when we want to travel on the level, the ups and downs, the waves in the Earth's surface, complicate the problem of getting a smooth, comfortable ride. The bumps and dips in the Earth's surface over which we travel have been reduced. Great progress has been made in leveling and smoothing out roads and highways. But automotive engineers have long known that all roads can never be made perfectly smooth. Even the smooth, paved roads have long, gradual waves, or small, sharp bumps that have different effects at different speeds. The wheels of our motor cars follow these waves, moving up and down with each change in the surface of the road. So, to give us the smooth, level ride we want, engineers knew that the smoothing and leveling would have to be done by the motor car itself. Between the moving wheels and the passengers, some sort of a bump leveling device is needed. Let's see for ourselves the method by which the engineers have approached and solved this problem. Here is a wheel, fastened so that it is free to move up and down. The wheel rolls on a moving belt, rising and falling whenever it strikes a bump. A platform, fastened solidly to the wheel, carries a tracing pen, and when the wheel moves up and down, the tracing pen draws a line which shows the movement of the platform. To get a true picture of the up and down movements, the tracing paper moves at the same speed as the moving ground belt. We'll start the model running. Now, the traced line gives us an exact picture of the up and down movements of the wheel and platform. Let's see what happens when we use more speed. At high speeds, the effect of a bump is considerably greater. In slow motion photography, we can see that the wheel climbs the bump and bounces into the air. Of course, this jolting is passed on to the platform. We can mount a fairly stiff spring underneath the platform to see how it will affect the jolting. Now, let's watch it in slow motion photography. The traced line shows that we have cut down the jolting because the spring absorbs some of the effect of the bump. Let's substitute a soft spring for the stiff spring that we have been using. A softer spring gives a smoother line because a soft spring is able to spread out the effect of the bump and act as a better cushion against the jolt of the wheel. But when there are 4 wheels mounted in 2 sets, front and rear, as in the motor car, the problem is complicated. Until recently, the front springs of the automobile had to be stiff to keep the axle and front wheels in line. If one set of springs is stiffer than the other set, the stiff set will bounce harder and faster. We can see that this unequal springing, stiff springs in front and soft springs in rear, causes pitching when the wheels strike a bump. The traced line shows this clearly. The only way to eliminate this unequal springing and make the front springs soft is to give them only one job to perform, the job of absorbing bumps. Suppose we replace the bouncing axle with a rigid, immovable beam. Now the wheels can be fastened to the beam by 2 parallel swinging arms. The wheel is pivoted so that even when the arms are tilted by a jolt or bump, the wheel remains vertical and in perfect alignment. And so now, in place of a stiff spring, we can use a soft spiral spring to absorb the jolts and level out the bumps. Since the rigid beam and the swinging arms keep the front wheels in line, there is only one job left for our springs to do. With both front and rear springs equally soft, the platform is held in balance. But now that the front and rear springs are soft, we have another problem. Springs that are soft enough to level out the bumps will compress too rapidly under a heavy shock. And springs that are soft enough to absorb small shocks have a tendency to continue bouncing after they have been compressed or stretched. So to help the springs absorb heavy shocks, we can slow down their action by means of shock absorbers. The shock absorber acts like a brake in delaying the movement of the spring, and it prevents bouncing when the spring is compressed and then released. We can make the severest kind of test to see whether we have a method that will really iron out the ups and downs. We'll use a lot more bumps of different sizes, and we'll run them under our wheels at full speed. Now watch the traced line. The traced line seems to be pretty smooth. Let's watch through the slow motion camera and see just what's happening. No more pitching, and the soft springs with their shock absorbers spread out the effect of any bumps that they can't completely absorb. Of course, in actual practice, where strength and safety are of maximum importance, engineers have made use of these same bump-absorbing, road-leveling principles with a much stronger and more durable construction. The front wheel is pivoted so that it can be steered in any direction and is mounted on a strong, upright arm. The upright arm is fastened to the rigid, immovable crossbeam by means of two parallel swinging arms. The swinging arms and the rigid crossbeam do all the work of keeping the wheels in perfect alignment. So the genuine soft knee action spring has only one job to do: cushion the bumps. A double action shock absorber controls both the compressing and stretching of the spring as it absorbs heavy jolts. This combination of soft cushioning springs, together with positive double action control on the front wheels, is balanced at the rear wheels by equally soft springs with the same type of double action shock absorbers for control. With soft, balanced springing, held under positive double control, the smoothing and leveling of roads is done by the motor car itself. The pitching and the ups and downs are eliminated. Here is a real test on a full-size scale. That pipe sticking up from the top of the car is a giant tracing pen. The sky itself will be our moving strip of tracing paper. And this tank of skywriting smoke will take the place of ink. The car rides smoothly over the waves, while the wheels do all of the pounding. Watch the traced line. And so, the pain in the neck has been taken out of ordinary driving, giving a truly level ride over any bumps on city streets or on country roads.